Alrighty, folks, welcome to our next module. We are starting with Module 7 and are going to be talking about textures today. So with that said, let's go ahead and dive into our website and just take a little look at what is going on here. So we'll be at Module number 7 and are going to learn about adding some nice detail to our scenes here. So with that said, let's go ahead and dive into it and talk a little bit about textures. But before we get into that, we're going to be talking a little bit about building an abstraction for our labs. So anyway, without further ado, let's go ahead and dive in. So for module number 7, let's go ahead and move along here. And a little pre-class warm-up today. Just talking a little bit about this idea of something called UV mapping. And it's a process for texturing characters or environments or objects in computer graphics. This is how artists create or map 3D objects to 2D images to give them even more detail. And you can kind of get a little bit of a sense of this from Blender. You can see where the user is moving some geometry around an image. And as they move it around here, you can see where the eyes sort of start to appear when the geometry is over the eyes. So this is exactly what's going on. We're going to learn about this process of texturing in today's lesson. But before we get started, I want to talk about other methods that are becoming more and more prevalent. And it's sort of automating this process of texturing. So I know many folks have done some 3D work in this class and have done UV mapping, but more and more recently in the last few years, tools like ZBrush, which is what's featured here, have often offered various almost spray painting tools where you can sculpt the model like clay and paint over it. So it's really kind of neat stuff that you can see here. But anyway, this is one here called ZBrush, and it's made by two gentlemen, or the company Pixelogic, that offers ZBrush, Offer and Jack, and is really kind of a cool, or was one of the breakthrough programs for allowing you to sculpt your 3D models. So for those folks who have completed assignment number 3, you've seen the part 2 is introducing you to some 3D work. There are many other tools or ways to do 3D work. So even if that didn't click with you immediately, again, those kinds of things take lots of practice, there are other tools and styles for doing 3D work. So just wanted to highlight that today. All right, so last lecture, we talked about OpenGL and doing some air handling. We talked a little about shaders and working with uniforms. And then we eventually talked about putting our scene into a perspective view with the MVP matrix, the model view projection matrix. Okay, and that's how we're going to set up our cameras and proceed forward throughout this course. So we showed this little handy function here, and hopefully that'll be useful for you. Just a little bit of logistics before we move on. So homework 3 is out, where you'll be loading object models, the .obj format. And again, your goal is to parse and display in both wireframe and filled in solid color a model. Okay, so you'll be working on that. Now for homework 4, that has also been pushed to your repository. Again, I'm trying to push stuff out a little bit early just to help give folks a head start if they have extra time or for whatever reason want to get started early. That is also out, and you'll be building in a textured object model loader. Okay, so you'll be doing what we learned today, taking that information and applying it to your object modelers. So I hope you look forward to that. So keeping that in mind for your homework 3, homework 4 is going to build on top of it. So, get an implementation working, but, keep in mind that you will be building on top of it with what you'll learn today, which is how to add texture coordinates to your models. Okay, so let's talk a little bit about abstraction here. So we've run into a little bit of a problem, or at least I'm going to call it a problem, in that our starter code for the labs is starting to grow significantly. So if I go ahead and open up, let's go ahead and just open up a new tab here and look at our code here, all the way through lab 6. And here's, let's say, part 2, where we were working on the colored triangles. Our code's starting to get, there's a lot going on here in this one program, and we're just going to keep adding to it. So we're going to want to start abstracting some of this. You can see sort of our boilerplate OpenGL here with SDL even is, 400 plus lines of code here. So we're going to want to start building larger programs and building up our abstraction. And it's totally fine to sort of do this, especially as we're learning, in my opinion, and sort of have this sandbox application where we can just sort of play and test out new ideas. But it's actually going to work out a little bit nicer for us as we move on to more advanced concepts that we can have a good abstraction. So, just as an aside, I've seen some very good engineers that I've worked with build huge, 10,000 line programs in one file. To sort of test out their ideas, learn something new, but eventually you want to refactor into something that will be more manageable, will compile faster, will make it less prone for you to have errors, and so on. Okay, so I just want to remind you about some C++ things. As I know, C++ is new for many. That there are header files, the .h file, .hxx, or .hpp files, and C++ files, which are the implementation files. So our header files only have declarations of function, and they sort of tell the compiler, hey, this function is part of the class, or here's how we make a data type. Here's the sort of blueprint for some custom thing that we want to build. And then within a source file, those are the actual definitions of functions that tell the compiler, hey, this is the body of code for how I actually execute the function, the actual implementation. Okay, so you're going to see some example header files in your lab today, like object, for instance, that have some member variables here for our custom type here, object. And you're going to have your member functions here that say, these are the things that we are going to want to do. So, again, notice there's no implementation in this file. There's no loops, if statements, any logic of any kind here. And this is a nice way to separate things out because I can look at and I can fit this, in one slide, or if you actually work as an engineer, you can look at this and fit it on one screen and see all the functionality that's available for this object here. So that's going to be really helpful for us. So in the implementation, however, of our object CPP, we can see the logic of the code here. Okay, so we could see in that particular update function that this is how we actually do the update. Here's all the logic, all the other function calls, what we're doing, and so on. Okay, so that's what's going on again in the CPP files. Okay, and just a little reminder, sort of C++ stuff, but here's the member function we're giving a definition to in our CPP file, which is called update. So if I look back here, this was update here. And then the scope of where I find that member function is an object. And it's always object : : is a scope operator. It's telling you about where you can find something. So update we can find as part of the object class. That's just sort of saying, hey, we're attached to this object. We're a member function here of object. Just to give you a little bit of C++ insight here. Okay, so a few other things that we're going to do. So at the top of our CPP files, we're also going to include our header files. Okay, in our implementations, these are CPP files. We need to include the class or the blueprint that says, these are our member functions, our declarations. We're sort of declaring them ahead of time, and then saying, what we're going to actually do. When you see includes in C++, you can think of this as copying and pasting code directly where the include is. And then during the compilation stage, when you're compiling your code, you're essentially doing a copy and paste of everything that's in this HPP file into your C++ file. Okay, so let me illustrate this by opening your support code for today in lab number 7. And let me make this bigger for folks. So if I just quickly look at one of our header files, we've been looking at the object one here, and I'll make it just a tiny bit smaller. Here is our blueprint, again, just sort of defining all the stuff that we'll have available, declaring all these things. But the actual definition comes in the object files. So the first thing we do is include that file here that says, hey, I have all these member functions available. I'm creating a new data type class, called object. And then here's where we are, again, implementing all those member functions. Okay, so you can just kind of see that here. Okay, so that's the idea there. Okay, and when we create our header files, there is something you may have noticed in them. Again, just on a show you the C++ isms and things so that we can move forward here. is that at the very top and bottom of the files, you'll notice these if and def, which are also starting with the pound symbol here. These are called header guards. So these sort of protect us from including this file multiple times, because we can only declare one data type uniquely. We can only do this once. We can only create one type called object. So if I include this file in multiple other files, for instance, like you may have seen with things like vector or string, we only should be able to declare it and define things one time. Otherwise, you'll get errors like that say multiple definitions for including something too many times. So anyway, so this goes in the preprocessor during the compilation stage and says, okay, if this isn't defined, this symbol, define it. And now it's been defined once. Do all this copy and paste into whatever file you've included in, and then endif, so the preprocessor. So then if it sees it again, it's going to check and say, well, okay, object underscore HPP, that has been defined before, so don't include this. And that avoids you getting any errors. So whenever you create a header file, you include these header guards in them. Okay, that's the safe thing to do. And it also avoids problems like if this file includes vector, but vector includes this file, it avoids that sort of circular dependency as well. Okay, so let's also talk about, since we're creating our own data types, our own classes, a little bit about object lifetime. So with this, whenever we're using our class, just to get some terminology, we're creating an instance of an object. So we have capital O object here that we are defining here, and then we can create an instance of it. We can have 10 instances of it, okay? So for example, we can create object my object here. And that's my object is an instance of an object with the type uppercase object here, okay? And then within object, we can have other instances of variables that make up this class, for instance, like m underscore shader would be an instance of that. And for example, we have a m underscore vertex buffer layout, which we'll talk about later, but that is of type vertex buffer layout, but it's just an instance of that type, okay? And it's also a member variable of this object class. And the scope of these member variables are that they belong to that object class, so they're available there. And something that you're going to see in the abstraction that I provide, and you can follow this or not follow it, it's up to your choice, is you're going to see me prefix these variables with m underscore. I'll try to be consistent throughout the semester, but for the most part, if I have something that's m underscore, that means it's a member variable. So I actually name my variables there. It's also easier in IntelliSense and for autocomplete and these kind of things to find those variables. Okay, so that's just a little bit about the abstraction going forward. Something to keep in mind too is you can also have, of course, pointers to any of these objects that you create. So you might see this on occasion in the code where you have a pointer to some object here. And then in order to set up our object, since it's a pointer, well, I need to allocate some memory for it. So I'll create a new object. So this would be one way where I can allocate a new object. And then I can access it and do whatever, call whatever member functions I want on m underscore object here. Okay, so using our member variables, again, here is just that example again, where this has been previously allocated. You'll see something like a render call, so it's calling its own render function here, this instance of this object here. And just a quick question to test your sort of knowledge of pointers or remind you. Why is there an arrow to call this function here? I'm going to give you a moment to pause the video and think about that. And the arrow, remember, is because m underscore object is a pointer, we have to dereference it and then access the member function here, okay? And the arrow is sort of a shorthand for us to be able to do that in just one nice function call here, okay? Or rather one line here. You can do the equivalent here. This is, again, if I put in parentheses and then dereference the object and then dot render, that's also equivalent in the C++, okay? Okay, so there's two ways you can write it, but just if you see the arrow or haven't seen them before, this is where it comes from. Okay, and a reminder on dynamic memory allocation, because if you have something like m underscore object, again, what is going on in this snippet here is that you are allocating a new object for it. Here with new, that's allocating memory on the heap. So that means the heap memory is accessible until we deallocate with delete. So this pointer points to some chunk of memory that's always going to exist until we explicitly call delete on it. Delete or the delete with the brackets if you have an array. Okay, and then this is the type of memory that's being allocated. It's enough memory for an object, to store an object in it. Now, if we don't allocate, or if m underscore objects has been assigned to null, so if we test, is this equal to null, will we get an error? I'll give you a moment to pause the video and think about this. And if you pause the video and thought about it for just a few moments, the answer is yes, you'll get a segmentation fault, right? So this will be familiar to folks who have done C programming, and then of course those of you who are doing C++ or have done C++ before. And again, a segmentation fault is just one of the most common errors in C++. So again, it means that we've accessed memory that we don't own. So again, if something is, again, pointing to null, then you can sort of think of this as the equivalent of just saying null, with the arrow, render, which doesn't exist in our code. Okay. So there are other types of memory in C++, or, well, really every programming language may or may not be as explicit, but stuff that's allocated on the stack. So if I just create some variable here, like verts here, glfloat and an array here, this is allocated on the stack. It's local. It's only accessible within this bracket and or this curly brace, this left curly brace and right curly brace, okay? So it'll be available within the scope of this constructor, but then it goes away forever, okay? So the same thing with indices here. This is sort of how we've been creating things previously, so we could sort of do this setup. And then, so again, this goes away though automatically, so it's not managed by us. And sometimes we might want these things to stay around longer. Okay, so that's where we need to use heap memory. Sometimes we don't, so that's also okay. So my question is, why is it okay in OpenGL? In this instance, though, if I'm executing this and I'm trying to create some, layout here where I'm trying to allocate some buffer and do, size of verts or whatever, why is it that I can do this and figure out, the size of this verts array here? Because normally I can't do that, but since it's been well, I'll give you the answer. Since it's been locally allocated here, we can figure out the size of verts here. Okay, we can we see the array directly right here, so we can change it. Okay. Now the other thing that's going on is, and this is going to be hidden a little bit in our abstraction, but I'm showing a example of some stuff I guess we've been doing. But this is the idea that we have this create buffer layout, which is doing this sort of glgen buffer behind the scenes, and it's populating the data here. So let me go ahead and just show where that's going on in our, well, this is going to be our new abstraction layer. Let me open up the source for it here and make it just a little bit smaller. But just to jog your memory, remember we were doing this sort of glgen buffer stuff with the vertex position. We had, a bunch of vertices. So this GL buffer data, for instance, and then we were setting up all the attributes. We're shipping this data when we make this function call onto the GPU. So it doesn't really matter if the data is on the heap or on the stack or wherever, because it's going to be on the GPU until we turn our machines off. Okay, that's the idea here. Okay, so this is okay that we can ship away stack allocated information as long as it's going on the GPU and being copied there. That's okay. But we do have to be a little bit careful. So I'm just putting this little gotcha here. And I believe this has been part of our exercises in assignment 3 if you've been doing the C++ stuff. But just want to sort of call this out. But size of is going to return different sizes for stack and heap allocated data. So we really have to be careful with the size of operator. I think it's just a little tricky thing to remember. So I'm going to just fix that gotcha. This is going to be part of our abstraction by instead just having a vector data structure, or you could use an array, but I think a vector really works best here if you don't know how many vertices you need. But this vertices here, we can push back other vertices, we can remove them, we can insert them wherever we want, and same thing for indices. And then by making this variable, moving it from local scope instead to be a member variable of our class, then this collection, these two data structures here, they're going to live for the duration of our object. So then we don't really have to worry about if they go away or if we need to send that data back to the GPU or make a copy or whatever. And it's just a little bit cleaner way to store the data. Okay, it's in an actual data structure versus just storing the sort of raw vertices. We've been doing some experiments with that, which I think is fine. But we really want to have them in a nice data structure for us to access things, okay? So I've refactored the code just a little bit. So it is still m_vertices, and I'm just initializing all of the vertices directly. But you could push back the vertices one at a time or whatever, and that's likely the strategy that you're using in your object model loaders, okay? So this is the idea. I'm doing the same thing with indices here, just populating, and this is for the to make a quad or a rectangle, okay? Okay, so note below, and I'm going to introduce this in the abstraction a little bit here, that instead of using the size of operator, then you can just use the data structure m_vertices and then dot size. And that really makes things a little bit easier for us to work with here. Okay, m_vertices dot size, no size of, no worrying about is this stack allocated or heap allocated. It's just part of the class. Okay. So that's really what the first bit here that I've been, why I'm reintroducing classes in this terminology is just for you to think about the lifetime of where your memory is allocated and where this will overall fit into our larger abstraction. Okay, so a little bit more on C++ if you need it. The classes section's pretty good for review on this, and dynamic memory for the heap allocated stuff. Okay, so let's go ahead and just talk about the code abstraction of the lab and our future labs that I've provided. So, the nature of this again is that there's a lot of boilerplate code that we have, and we've handled a lot of it through SDL as far as like creating the window and OpenGL context and setting our version and all those things. But we really want to start abstracting away some of the other, stuff like generating these buffers, and it's going to allow us to get to some more interesting graphics techniques rather than, having to set up everything from scratch every time. At some point we have to be building, and this is our goal, to build like a little graphics engine that can do some, neat stuff, or at least display a few models and objects. Okay, so we're going to build a little API, a little application programming interface for our graphics framework, and you might further develop this and later on in the course to have extra functionality, but I also want this to be a little bit of an exercise for you to learn how to build a sort of good API that's sort of consistent in how we name things. It'll help you prevent errors, and again, it's going to let us expand and build more interesting stuff. Okay, so let's go ahead and look at what we have today. And for some folks, this might be a lot of C++ code at once, so I just want to show you how to explore it and give you the high-level view of our abstraction. So if you go into the Lab 7 folder and just type ls, you'll see our folder structure. It's pretty much the same here. We have our build file. We're going to have a cat texture today for today's lab. You'll see it later. We have our include, where all of our .h or HPP files are. You'll have SDL2 DLL for folks to have that. The shaders folder for vertex and fragment shader, the source folder, and then you have your common third-party library where GLM is. Okay. So anytime you have a new or large code base, the right thing to do is to open up a terminal or whatever your tool is, cd into that folder. So here's our Lab 7. And I typically like to look into an include folder, do an ls, and see all of the HPP files. Okay, why? Again, this is actually a nice feature of C++ is because you have the blueprint right in front of you. So I can open up, I'm just going to choose one of these randomly, transform, which I don't talk about explicitly in the slides, but you can see that, okay, this is a transform, it's going to hold, some transformations, some stuff that's familiar. Okay, load identity, translate, rotate. Okay, so it looks like it's working with a 4x4 matrix. This is sort of how I'd be thinking about it again. And indeed, there is a transform matrix. And yeah, there's, this is basically a giant wrapper around a GLM 4x4 matrix with some helper functions to make it, easier to work with transformations. Okay, so that's sort of the idea here. You can abstract this however you want. You could just use raw matrices for everything, but it's nice to just have a single transform class, and then this can become part of your object or whatever other entity that you have, whether it's a 3D object, maybe it's a camera, which we'll talk about, maybe it's a light source, just something that needs position in a 3D world. So anyway, that's how you can sort of explore this and at least look at the header files to get an idea of what is in the API. Okay, so to start, we have our SDL graphics program .hpp. Again, this is just our interface for creating our window, handling our input. This has been pretty much what we've had the whole entire semester. So you can see what this looks like. It's just been cleaned up a little bit to have m underscore, everything, and sort of similar capitalization and some of these things that just make it a little bit more of a consistent API so you can see what's available, okay? And what you can see is on line, I've changed it here, 57, that our SDL graphics program just kind of snuck in for now that there's always going to be one object in our scene. Okay, I've just kind of snuck this in. Maybe we want a little bit of a better interface for this, for our SDL graphics program, maybe like an add object function or, something like this to, make things a little bit cleaner in our abstraction. But for now, every one of our graphics programs is just going to have one of these objects. And this is for the purpose of the lab right now, okay, until we learn about other data structures. Okay, so let's look at some of the other header files, and one that I've already given you a brief sneak peek is this vertex buffer layout, okay? And the problem that this class is trying to solve is just to make it easier for us to pass information to our shaders. That is vertex information that we're passing into our shaders. Again, so if we're trying to figure out, hey, does this have position data? Does it have normals? Does it have texture coordinates, fog coordinates, multiple textures, whatever information that we think we might want to pass into our vertex shader, this is going to be our class that just makes it really easy to say, okay, I need a vertex that has an X, Y, and a Z position, or maybe just an X and a Y position. Okay, if you're trying to choose between 2D and 3D. So it'll have helper functions like create position buffer layout for creating the layout for an X, Y, Z form here. Okay, so that's it with it. Okay. Okay, so within our vertex buffer layout, we're going to have, vertex arrays, vertex buffers, index buffers, and so on, okay? And again, as I mentioned, the create position buffer layout with X, Y, and Z positions for our vertices, or create texture buffer layout with X, Y, Z. And as we're going to learn about textures, we need two more coordinates here, S and T. So that's automatically going to take care of setting up that layout by pushing another attribute to our vertex with texture coordinates. So within the layout, what it's going to have is the member functions, that we're sort of implementing here is, it's just taking care of us avoiding to have to write every object that we create, GL enable vertex array 1, and then set the pointer, and then figure out that it's an X, Y, and Z, the type to float, setting the size of everything, generating the buffer for the index buffer, the vertex buffer, setting up, a second attribute, and so on. So it's just going to take care of handling those sort of errors that we have. Again, so that's, again, the idea of building a good API with a good interface to clean up these things. Okay. So the key idea to this function here is generating the right buffer layout here. Again, as I've just sort of shown, but here's just a bigger snippet of the code. This is what you observed earlier too, where we did the same thing with our colored triangles, and we had to add an R, G, and B position. So we could have a totally separate layout for that, where we have objects that have XYZ positions and then RGB positions. Okay, so then you would know that the stride would be 6 in that case, because you'd have an RGB value as well as an XYZ, and you could set up the second attribute as well. So again, what if we want different buffer layouts? Simple, we just add another member function for creating that layout, and then it's all set. And then per object, we can just select or swap between different layouts with different data to display different objects and information. Okay. Now our abstraction here could be improved if you take a sort of deep dive or a deep look into the vertex buffer layout, meaning that you could at runtime, for instance, you could decide for your more so for your vertex buffer if you want to add an X, Y, and Z, or add an RGB, and sort of dynamically create this structure where you're adding attributes to it. I will leave that to you if that's something that you want to explore, or if you're going to be working with data that might have a lot of different vertex layouts, meaning some of your data is going to have an X and Y, some's going to have an X, Y, Z, and just a R color channel, or a single color channel, or all these different permutations. We could certainly make the ability to create different vertex layouts. We could certainly do that. For now, in this course, it's going to be enough to just every time we add a new feature, define a new one. It's also going to give us some practice at building these things and still using some of these functions as well. Okay, so another abstraction that I want to introduce is the shader header file, because again, we had a lot of these sort of free functions like create shader, which just did all the shader work. So again, we could wrap that into a class just to clean things up a little bit and avoid any mistakes, instantiate several different types of objects, and just have everything sort of nicely wrapped together. Okay, so here's our data type for representing shaders. You can see some of the function calls for loading shaders, creating the shaders, and so on. Some of these things like compiling shaders and so on, which is going to be similar for all of the shaders, and something that we might want to automate to make sure that we always compile the shader, check its linking status, print any errors, and so on, will be helpful. Okay. So there's a shader and a destructor, as always, but the create shader is really the important function here. Okay. And then we have a bind and unbind function. Now within OpenGL, if I look here, let's look at the docs here. I don't have a GL. If I just look at bind here, I sort of search through some of these. I don't have a, I don't really have a GL bind single shader. Instead, I have GL program or GL use program, right? This is for my shader, which is the equivalent of binding. So again, part of our API, just keeping things consistent, is just to go ahead and make a bind member function. So this is just sort of consistent in our API. It's kind of nice to do this, okay? So we just use bind here. Okay, and then the other functions of interest we're going to have, because we started working with uniforms, is that we can define a bunch of these helper uniform functions for setting uniform values, which is just doing one function call instead of two. So for example, if you remember with our uniforms, what we'd have to do is do a GL uniform location. So we, for our particular shader, get the name of some symbol, and then we would set that particular symbol or value at that particular location, and then sort of walk through, whatever the other steps are. So in this case, we can just make things a little bit easier by just creating these sort of set uniform matrix functions here. We'll follow the same sort of naming convention for floating point values here as our GL uniform matrix function. But again, we'll just have a bunch of these sort of set uniform functions to make things a little easier to work with in our shader, a little bit less error prone. As I mentioned, you had to be really careful with some of these things like setting the name and some of these things. And we can add some extra error handling for these types of things as well. Okay, so overall, it's just going to be a little bit of a cleaner interface, right? One line instead of two. So that's the idea here. Okay, so we aren't going to have all these sort of creating these integers here for this particular model transform matrix and then setting it 2 lines. Just one function call here. Okay, and then this is sort of the big one here, object.hpp. It's our new header file. Again, the problem that it's trying to solve is, again, to make it easy to create several 3D objects in our scene. You've seen a brief preview of how we can create just one object in our STL graphics program. Well, we could have a vector of those, or create 2 of the objects if we think we might need 2 or whatever, and that's pretty easy to do. And each of our objects has their own shader, their layout for however they're storing the data, potentially a texture that we're going to learn about today, transform, its own sort of how it's going to be projected, and all these sort of things here. Okay. And it's got a common interface, so you're going to see this sort of, we'll have an update function and render function. So that's similar to our STL graphics program. Again, just a good idea to consistently name things in the API again, so you can kind of see how this is being built up. Okay, so again, these are just some of the things that sort of make sense to me to have an object HPP. But a question you might follow up is, say, from a performance standpoint, are there any problems here? If I have, a shader per object and a vertex buffer layout per object, what do folks think here? I'll give you a moment to pause the video and think about it. And if you've had some time to pause and think about it for a few moments, it's possible, if we have a lot of objects in our scene in this sort of graphics framework, that we're going to be, recompiling that shader a bunch of times, maybe duplicating vertices if we have objects that are the same. So, we could be more efficient here. So for now, I'm going to say that this is okay. This is all done at runtime, but this is still our sandbox. We're still going to keep building on top of this. So, the aside here is that you'll probably have a manager class. So for those folks who have taken or are going to take these courses in software engineering or building game engines, we learn about building manager classes. So you can just load that shader one time and then reference it from all of your objects, right? Just have a pointer to it. That would also be an optimal or a fine strategy. That's what your graphics engines for folks who have used Unity or those types of tools are doing, right? You're not recreating the shaders over and over again, because that means you have sort of many different pipelines, lots of context switching inside of OpenGL and so on. So we could expand on that. For now, we're introducing enough new stuff today. Okay, so with that said, before we get on to more new stuff, give yourself a little break if you need it, and then we will continue forward. All right, so let's go ahead and continue moving on. And I want to talk about the shading model so far. Let's talk about our second topic. We've talked about the abstraction, but let's talk about how we've been coloring things in so far. We had our colored triangles last time, which was very, very beautiful. If you look at these triangles here, they now have some colors. We talked about how they sort of got interpolated. But we could do better, right, than our shading. It's very flat. It doesn't pop. It doesn't have much life to it, right? It's just an orange triangle here or a colored triangle here. It has a very matte feeling, we would say. It doesn't pop or glisten or reflect or do much of that. It just feels very flat here. What we're going to start moving into is this idea of building a sort of framework with some more advanced lighting here, but we want the actual final color of our triangles to be determined based off the angle that the light source is hitting that actual surface. So here's the normal to some flat surface. Here's the angle the light's coming in. Depending on the angle, well, we use our tool, right? The dot product here. Dot product of the normal dotted with the light source, where it is coming in, the vector from the light source to the normal. That gives us an angle, and that tells us how much we should color or shade in this particular normal here, okay? It tells us how bright stuff is. So for example, if the sky, in this case, the sun's being occluded, so it's being blocked by the clouds. So we might say something like, that's going to dim how much light is, hitting this surface here. That's one way to think of it. So we're going to have to dedicate, an entire lecture to that very, very, very soon. But, instead of just for now, building this sort of lighting model and introducing lights, we're relying purely on just the vertex colors, and that's still not enough. Okay, so before we even get to our shading model, we want to build something sort of interesting to add details. And for that, we're going to add textures. Okay, because most of the objects in the world aren't featureless. They aren't just, bright or dark or a single color, right? Trees have sort of grains to them. Your skin, this elephant's skin has wrinkles. Metal has little indentations into it that you can look at that sort of make things interesting, right? And if we want, we could go back and do this all in triangles, right? We could model this brick wall, but it's hard to capture some of this detail, the bricks protruding out or in. There would be much details here. It even says high polygon modular wall, so that means it's very high detail. So that's one problem here. Just the processing power needed to capture this detail with a lot of triangles. But we're still not also taking advantage of perhaps all the colors that we could. Okay. And the geometry to ask an artist to sort of model all these different shapes with all the indentations, even if we have nice sculpting tools like ZBrush, which we talked about at the very start of the class, it would take a lot of time. So instead, what we could do is just use two triangles and draw an image that a photographer has taken or that an artist has created, or you've sourced from some other image, and just sort of paste that across a triangle. Okay, so for this particular brick wall, this is just two triangles. This previous brick wall here, I don't have an exact poly count, but it's probably in at least a range of thousands, if not tens of thousands, or hundreds of thousands of polygons here with the amount of detail that they have. So instead, with only two triangles, we can approximate this brick wall shape pretty well, and it'll still look pretty good. Okay, you can of course have multiple textures in a scene. So here's multiple sort of brick walls. Now this image is a little bit dated, but I would still argue that it's more interesting than just looking at flat colored, quads here, rectangles here. And then I can, improve this by adding higher resolution textures here. So even in this very old image, it still looks pretty good, right? And it's just a few triangles here. 1, 2, 3, 4, 5, 6, only 7 really being rendered at once here. Maybe this one's divided here, so maybe 8 triangles at most. So that's pretty darn good for the quality of the final shot that you're getting here. And yes, I know we can do better, but this is just showing the amount of life that textures give to your scenes here. Okay, so now how do we draw on each of these polygons though to get this detail though? So the idea is, instead of going through the sort of rasterization process and just coloring in one sort of pixel at a time of a fixed color, instead what we're going to do is sample from a texture as we perform that rasterization. Okay, so our shaders are actually going to do this work because they're much faster. This is what a GPU is good at. They're going to look at the texture coordinates u, v for our color data. Okay, so here's u and v. You can think of it as x and y if you want them a Cartesian coordinate system, but really u and v is what we use to sort of delineate with, are we looking at a texture or just a image. Okay, so there is a difference between a texture and something that lives on the GPU and you can sample from using u and v. And the idea is, what we want to do is map every point that we have. So remember, our triangles are an x, y, and z, but we want to map them to a u and v point. Okay, so this particular vertex here, this vertex here, this vertex here, this vertex here, right? I'm mapping them on a Cartesian system here, so I can take this x, y, and z and map to this shape here, okay? And we can even think about this a little bit backwards, right? So my thought here is, wait, aren't we mapping the texture to the surface? Yeah, and again, here's how we sort of think backwards here. Maybe you've done this experiment, and we could do this in class in person someday. But if you've ever printed out, this sort of image here of a dice here, you can, cut out the white portions here, and then you can fold this into this cube shape here. So what this is exactly showing is, we need to figure out how to deform a 3D shape into a flat 2D image, and then we can just draw a texture on top of it. Okay, so our texture just ranges from 0, 0 to 1, 1 here. And then we're saying, hey, wherever this triangle is, this thing that we unfold, this 3D shape here, plot, wherever these triangles are going to be to this location, and then just sample from this location from these texture coordinates. Okay. So this is a process called UV unwrapping, where we're unfolding a 3D object into the UV coordinate space. Okay, so here's a nice visualization of it that's worth 1,000 words of taking a 3D object. So you can watch it go, let's see here, from the 3D, and then we're going to unfold it and figure out where that geometry would be in the 2D space and where to color it in. So sometimes an artist is literally doing this. They're selecting edges and vertices and sort of plotting them out on a 2D plane, and then you can color them in from there, in a Photoshop program or, using other tools. That's how it sort of works, okay? And the UV maps themselves can get quite complicated, right? This guy here, whoever this is, you can see there's a lot of detail even in this simple image, and you can have multiple images to texture one character. Okay, so you can kind of see where they've selected here on the left side and what the colors are. So this shoulder blade, for instance, has been laid out in this sort of pattern here. All the detail, right? And it's a 3D shape, so it's been laid out in 2D, however. Again, so it's been unfolded. So if anybody's ever done origami before, you sort of understand this idea of paper folding, but taking a 2D shape and making a 3D shape, a 2D plane into a 3D shape. This is exactly what's going on, except you can sort of think of it backwards, okay? Now for us, for the most part, we aren't going to have to do this because our object files that we load are going to have these vertex texture coordinates specified for us. Okay, so per vertex, where is the sort of start, and for each of the vertexes, where is the sort of ending point, and so on. So this information is captured for us, which is very nice. Okay. So again, getting this mapping done correctly is done by artists, okay, in the 3D programs. We're not going to have to we're going to have to utilize this data, but we won't have to generate it ourselves here. Now, one thing to keep in mind though is that doing this process of a 3D to 2D shape, or 3D coordinates to 2D, right? It's a mapping, and we could have some distortion. And in some ways, this might be unavoidable. Our globe, if you've ever looked at a globe and seen it, that's, somewhat, accurate, right? This is our sort of world here. But when you unfold it onto a 2D shape where you're actually painting it in, if anyone's ever seen this, I remember as a kid looking and saying, wow, Antarctica's, massive. You see it sort of stretched out here. This is because of distortion. It tends to happen at the top or the bottoms of images because these areas that you unwrap, see this very small area, unwraps to an equal size here on the 2D image, so you get this sort of distortion because something's being projected in a larger sort of space here. Okay, so cartographers or map makers have struggled with this problem forever. This idea of surface parameterization, that is, how do I take some surface here, S, and map it to the texture coordinates. That's parameterizing X, Y, and Z to UV coordinate, okay? And there's a couple of, key problems here. Again, not that you'll have to worry about it, but if you go into 3D or build some of these tools, you might have to. But the key problems, again, the bijectivity, making sure that each point on a surface maps to a different point on the texture, right? You don't want, if you're coloring in the US to, be the same point as some other country here, right? If it's supposed to be represented differently. So that's the idea of bijectivity, one-to-one mapping. The size distortion, again, is an issue. That's what we saw with the globe, sort of stretching it out on this plane here. Some different representations try to do better, like this sort of representation here of the globe, or Antarctica is maybe a little bit smaller and you're sort of stretching the texture, but again, it's still not quite right. And there's other issues here, like the continuity, making sure that there's no seams in the images, and so on. Okay. Anyway, so those are some of the issues that cartographers have wrestled with for a long time. And if you ever wondered why, when you look at a globe and then you look at a 2D map, the countries are different sizes, it's because of this issue of distortion. Okay. And this has to do with different ways that you project textures. Again, the projections are a way to sort of approximate your UV coordinates. You can use sort of different styles, planar projections. The globe was sort of a spherical coordinate projection where you took a sphere and just sort of mapped to the 2D coordinates x and y between a range of 0, 0 to 1, 1. But if we just want to look at a quick example here, a planar projection is if I sort of took this cube here and pretend this is a piece of paper, and I just push this cube through the piece of paper, and you can see here's the texture that was applied. Well, the front face looks pretty good here because I'm just sort of pushing it into it. But I'm also stretching the paper, around the rest of this cube. Pretend this is sort of a stretchy material or a cloth or something that you're stretching. And so you can see how this distortion happens at the top and on the sides here. So the mapping on the front face of the cube is perfect, but then I've got to stretch this cube all the way to the tip here, and that's going to stretch out the numbers. So you'll often see folks when they're doing these sort of experiments use things like numbers or checkerboards or stuff just to see or try to detect if there's any distortion in their algorithm or their tool. Okay. Okay. So again, luckily, object files, are going to explicitly state the coordinates for us. Okay. And then the texture projection can then just be interpolated. So we'll just specify a point here, such as 0, 0. Maybe this is -1, -1, and this is 1, -3 or something, and it'll just interpolate between those points here and do the rasterization for us along this texture here. Okay, so just plotted this point here. So for this vertex and this vertex and this vertex, so here's 3 of them that make up my face. So what it does is it plots those onto a 2D image with a range of 0, 0 to 1, 1, and then does the mapping here. So if you wanted to make a really, really simple UV mapping tool, that's essentially what you would do. You'd have on the right side your object, and then per vertex, you would sort of specify the coordinates, and they would plot them down here on a per triangle basis or per face basis, and that's what you would have. Okay, so here's just another technique here showing the distortion here. This one, all the triangles on the actual geometry are the same size, so you can see how they get away with not having any distortion here, which is pretty nice. Okay, looks pretty sharp. So again, from it, it's not perfect though. From a distance, you might not see all the details. You might have to use a higher resolution texture to get more detail. Just some ideas there. Okay. Now this is something I'm really excited about because I've wrestled with this idea and always wanted to build my own UV mapper. Haven't gotten around to it. I just think it's a really fascinating art and sort of interested in sort of the origami stuff. But let me show you just a quick video here. It's a little bit of a divergence, but just something I'm excited about here. But this tool here that does the automatic unwrapping. So anyone who's done 3D work extensively will appreciate this, but here's some mesh here, and you can see how it automatically unwraps the entire model, sort of minimizing the amount of distortion and keeping things in sort of proportion nicely onto a 2D base here. And I just love the actual presentation here, so let me show it one more time here. So taking this, something relatively complicated like a human and just unwrapping it on 2D. And then an artist can paint in here, your jeans, your t-shirt color, or whatever, and so on. So let me see if I can find a couple more cool ones here. So it talks about what this algorithm is. And this is, some ideas of, state-of-the-art research and some stuff, some problems that still exist and continue to exist in 3D graphics. Just for folks that are interested here. Let's see here. We can find some other. I won't mess around with it too much. Let's see, here's another one here. So you can see some of the issues too here are we have to sort of sometimes relax our constraints, because if we're painting this in, if we're an artist and one article is overlapping or there are seams between them, you might get some color bleeding into the other one. So you have to be a little bit careful here. So this is talking about, you know, the different techniques you have there. This is taking this shape here and kind of stretching it, because you also don't want to leave too much empty space, because you know, you only have so much video memory or so many pixels to work with. So you want to fill it up optimally. So it's kind of an interesting challenge here. Let's see if we can get one more animation here. Maybe I'll jump to some of the earlier things. So this is showing, you know, the early experience UV mapping and just how terrible it was. So that's what sort of motivated this person. You know, so here it is. This is kind of cool. So here's automating some of that here. So really neat talk here, worth watching here. Oh, here's some of the different interesting shapes here, and how they just sort of unfold. So then they build into, you know, more complex stuff. Super cool. Okay, so that's a little bit of divergence, but just, you know, if you want to think about, you know, state-of-the-art stuff here, this would be, you know, 2018. So it'd be interesting to see some of the you know, later developments on this. I'd certainly be happy to share some of those or look into it if folks are curious. Okay, so we'll jump back into the texturing stuff, but a few other things that come along with texturing is this idea of mip mapping. So not only do we have textures that we want to generate, but we also want multiple levels of detail for the textures. And what a mip map is, it's going to take your texture. So it's not enough that we're just, you know, wrapping these textures on each of our triangles, but we're actually going to wrap these textures on our triangles, but also generate that same image at different sizes. Okay, and you might be wondering, well, why does this matter here? Well, typically a further away object, you know, if it's using a higher level of detail version of a texture, that might be a waste, right? So we can get away with the same sort of detail with a lower level of detail here. So here's an example. Here's a nice example of what mip maps look like. So here's a game here, and you can see the highest level here. You can actually see the cutoff if you look closely. Now, when a player is moving around in this game, they're less likely to see this sort of shift here, right? You don't really internalize it or perceive it when you're moving, right? These shifts between the level of detail. But here you can definitely notice, here's the with no mip maps, so where everything that's rendered, regardless of distance, is the highest level of detail. Okay, so again, this is just a kind of fun example that, you know, made me care about mip mapping more when, you know, it was something I didn't even think about in graphics. And for us, it's just going to be something that when we create our textures, we're going to enable mip maps so that, you know, regardless if they're really far away, they'll render quicker, because let's go ahead and look at this, right? Only, you know, 32 by 32 image that has to be displayed versus the full detail image. And, you know, this is just basically by powers of 2, it'll decrement it. It makes those images for us. It's very nice. The hardware does it for us. But the other thing I thought about with this, and this will be more relatable perhaps to photographers, and I'll ask you the question, you know, where do you really care about having a high level of detail if you're shooting an image? And you'll see this a lot on, you know, your, I'm not on Instagram, but, you know, those kind of photos, or when you look at National Geographic photos or portraits or these kind of things, right? You sort of have these images here. The bottom one shows it nice, where the detail is what's close, right? That's what you care about. This is something called depth of field, where you have a very sharp focus on objects that are close. So the distance between the nearest object and the farthest object, you know, you very sharply increase the detail or the resolution of the closer object, and everything that's further away is kind of blurred, okay? So that's where that comes from. And then in games, you see this all the time. Now, you know, these aren't necessarily, these textures are being mip mapped so that are further away, but we're also sort of blurring and thinking about, you know, what the player cares about? Where do we want to draw the attention to? Well, it's this figure here in the foreground, right? So there's a little bit of composition, and you can think about photography if that's been a hobby of yours, and computer graphics and some of these things, how they apply to the final scene. Anyway, I thought that was kind of neat here, but let's go ahead and just update our texturing support in OpenGL, sort of updating our abstraction here. And we're not going to complicate things too much. We can have multiple textures per object, but let's just go ahead and start with one. OpenGL does allow you to have multiple textures. I'm going to just give you some sort of some code provided in our abstraction here and walk through some of the steps here that you're going to have to actually finish off here just to figure out some of the new pieces. So here's our texture class here. And again, it's sort of the same consistent API where we're going to bind textures, unbind things, giving a load ppm image, some helper functions and so on. So we'll have our sort of constructor to build the thing, and then the load texture, which will load a specific image that we want to create. Okay, so here's what load image looks like. It's going to have a lot of familiar ideas to it. So we have glgen texture, which makes a buffer for our texture. So these glgen functions are becoming a little bit more familiar. glgen buffers, glgen shader, glgen vertex buffer, and so on, or glgen buffers. So it's the same idea here. And then we bind to it, so that selects it and says, hey, this is the texture that we want to work with. Okay, we don't have, OpenGL is a C API, so we don't have classes or anything, so we just sort of select something by binding to it. Then, since whatever we're bound to, we'll change those texture properties for our textures here. And then finally generate the texture. So there's GL text image 2D, and this is what actually creates the texture on the GPU. Okay, and then we just unbind to it by binding to texture 0 here, which just says, hey, we're not bound to any specific texture here. Okay, so two key ideas skipped though on load ppm and pixel data. Not really skipped, but they're just old ideas. So remember, I'm taking care of in load ppm, just working with the ppm format. Okay, so something that we've already looked at before here. Okay, so now all of our objects in our program are going to have a single texture now. Okay, so you'll see that that's added to the list. So we have shaders, we have a vertex buffer layout. Now we have a texture. We'll have a transform and a sort of camera per object, I guess. Or projection, how we want to project it, rather. And then in our object CPP file, here we can see where we're binding to that texture. So every time we want to work with our object, again, this is part of just building our abstraction nicely. We're going to have, we're going to bind to our layout. So say, hey, we're working with these vertices and indices. We're working with this texture, and now we're working with this shader, and then finally draw our object. All the triangles, all of our indices, right? So this is nice. We just have that vector here, so we can just do dot size here. We'll never make a mistake. And then that's all we have to do. Going on within the texture bind, if you want to take a look into it, we're enabling OpenGL's ability to use these 2D textures, sort of set the active textures. So we're enabling texturing in OpenGL every time that we bind, setting the active texture. As mentioned, we only have we're only working with one texture, so the slot here is really 0, but we could have multiple here. And then we bind whatever our texture ID is that's been generated. Okay, so this seems pretty well so far. We have a texture, we've parsed the ppm, generated the texture, bound to it, and so on. So what are we missing? Well, our texture coordinates and our shader. Okay, so again, we need to have position for our vertices and texture coordinates. Okay, so we're just texturing a quad here, so we need to select our texture coordinates that cover this entire quad. And again, those ranging from 0, 0 to 1, 0. We can do this manually. This is easy enough to sort of analyze here, because our texture coordinates are going to line up relatively close to whatever the vertex coordinates are. Okay. All right. So in practice, this is what it looks like. So this is what you're going to have to implement in a function called make texture quad to add the texture coordinates. I'm going to zoom by it and you can reflect on it. And then you're going to have this create texture buffer layout, and it's just going to take in whatever the vertices that you have, the indices, vertices data. I should probably rename this indices, vertices, the array data. So you can just access the raw array from the vector here. And the same thing from the indices. Okay, so our verts data is now x, y, z, st. Okay, for the textures. St or uv, those would be the common ways to refer to the texture coordinates. Okay, so now remember, nothing really gets drawn until it hits the fragment shader though. Okay, so our shaders still need a little bit more information here. So we need to set up some uniforms here. So in our object update, we're gonna have a uniform that passes a value from the CPU to the GPU. So after we've bound our texture, we then say, hey, GPU, I have a texture, and I want to refer to it as u underscore texture because it's a uniform, so u underscore. And it's going to be in the first slot here, okay? So this is how we set a uniform for a texture in slot 0. And what we want to do then in the fragment shader is create something called a sampler 2D, because remember, what a texture is. It's something that we're sampling colors from, so that's where sampler comes from. 2D because it's two-dimensional. We could have different dimensions, that is allowable. But this is just a 2D texture. If you want to think of it like an image, it's just a texture is an image on the GPU, and we're sampling from it. Okay, we're sampling color data from. Okay. And again, this is a uniform because we've passed it in from our CPU. Okay, so in our vertex shader as well, we need to make sure that we're passing in the texture coordinates. So we need to update the layout. That'll be a change you need to make. And then you should observe too that we have an output from our vertex shader. We're outputting the texture coordinates. So for each of our vertices, because remember the vertex shader runs once per vertex, we want to send out each of those vertex coordinates that we're reading into our fragment shader, so our fragment shader can appropriately texture things. Okay, here's what success looks like. I will go ahead and show you an example. So I'll go ahead and run an example so you can see live. You should see something like this when you are finished. And you're welcome to change the texture if you like to something else. Just make sure to push it into your repository. Okay, so your task for the lab is going to be to fill in the make texture quad function, add the texture coordinates, fill in the vertex shader, making the updates that I've provided, and then add in the sampler 2D for the fragment shader so that we can sample from the texture information. Okay. Okay, so a little bit of more stuff before we wrap things up here. And of course, there'll be an in-class activity, but just some advanced textures, because I want you to also think of, we're sampling from a texture data, so we can also use textures to store other data than just color, okay? And this is a really, really powerful idea. We're gonna have a dedicated assignment to this, so just giving you a little bit of preview here, that we can store information beyond just color, okay? So previously what we've discussed is something called an albedo map or a diffuse map that just directly describes the colors, what the colors are in an image. But there's other maps such as normal maps and bump maps, okay? So let me describe these. A normal map is going to consist of a bunch of normals. So recall that a normal is a perpendicular vector from some planar surface. So there's a vector that sort of sticks out of a plane. So you can think of like a hedgehog that has these sort of perpendicular spikes poking out from it, okay? And depending on where these normals point, again, we can determine how much light an object receives. So you remember our little shading model example. We had that here. So, from our light source to this plane, and the light might scatter, right? That's why you see many different arrows here to wherever our camera is, but we can use this information, okay? But the idea is we can actually store this information in a texture. Okay, so here's a normal map. Let me see if I can find a better one. This one's actually pretty good, so I've replaced that other image, but So here you can see just the color map here, but here you can see sort of the information that's been encoded here. So we've actually got for each of these little, indentations in this brick here, we can actually encode an X, Y, and Z position for where the normal is at a per pixel level, or we call this at each texel. So a texel is an individual pixel RGB value on a texture. But we can see how sort of depending on the quality of the normal map here or how exaggerated these features are, we can get more bumpiness in our object by changing how light reflects on this object. So it's going to have more shadows or more light depending on the geometry of the surface, and it makes a much higher quality image. Okay. So here's a normal map again of a brick wall, just showing how much light's received by each brick based off of where that vector is. And again, the idea is, this is a texture here, but it's a specific kind called a normal map. So we will be able to have multiple textures on our models, but some of them will have different information. So this is just showing per fragment or per each little pixel here that the normals might be slightly skewed in different directions. And we want to be able to capture that information here. Okay, it gives the surface more bumpiness. Okay. These images sort of look blue because the Z vector is facing out towards us. So the actual image is going to show up, sort of similar to the actual color map or the diffuse map. But again, it's just encoding the X, Y, and Z position of the normals. So it'll look like something, very similar to what the actual color map is. Okay. So here's just the difference in image quality. Again, I showed this on one of the first lectures in the class here, but you can see the additional detail with the normal map. This one doesn't look like it has much of a texture here. It's kind of grayscale, but just the immense difference. And you can see how the light's sort of moving around somewhere in this scene and how that's actually captured here versus this one, which is just captured on this entire surface here, just the two triangles sort of moving across it. Okay, makes a huge difference there. So just a little bit more explanation on normal maps. That's what we're going to be moving towards after talking about the texture stuff. But I want to wrap us up here because that's plenty of stuff. And remind you to do your in-class activity, and we'll continue, moving on from there. So hopefully this is a fun one. We've got a nice sort of abstraction framework here, just looking back, that we'll be able to build some more interesting graphic scenes here. Starting with the texture here. So let me just leave it on what your goals are, and we will chat soon. We'll talk to you folks very soon.